hours, and they keep coming in droves. Yeah, I should get some new students potential students over to help lift this crap. Okay, so we are recording, so while that's all happening, let's talk about this midterm a little bit. Midterm is going to be on Friday. So Friday this week. You will have the entire class period to work on it. I'll design the exam to take about 30-35 minutes. So it should not be a horrible time stress.
It's upside down.
It's upside down. I can't get it in, Abe. Also, that's a HDMI port. Remember, we said I was a doctor of computer science here. So I'll design it to take about Gorilla. Is there good stuff on here?
Photography class.
Format?
I would be so mad.
Would you? Like, would you really rage?
No, I could throw your laptop if you want. I can rage that way.
Okay, there we go. So in any case, exam will be designed to be about 30-35 minutes, so there shouldn't be a time stress problem unless you don't know what you're talking about. It'll be essay short answer, so no like multiple choice or any stupid crap like that. So here's the topics it covers. We'll go through each of these. If you have questions, you can ask them now. Otherwise, you can come with questions on Wednesday. I'll be happy to cover those. So this kind of deals with all the grand level topics that are going to be on the exam. So anything we talk about beyond these or have talked about beyond these will not be present on the exam unless I change my mind. So what are operating systems? Hardware versus the operating system versus application programs versus users. So kind of the four constituents, if you will, that belong in the operating system and how those differ from one another. Goals of the operating system. Historical operating systems from Microsoft and Apple. Bootstrap program. That's that piece of software that goes from, hey, I'm just a piece of hardware to load a real operating system. Kind of a micro operating system in the middle. That's the bootstrap. Computer system organization, so memory, CPU, disk controllers, graphic adapters, again, only at the high level. The second half of the semester, we'll be talking about the details of each of these. I/O and CPU execution correlation, so the idea of a CPU possibly getting interrupted to deal with I/O operations, things like that. USB. We talked about kind of parallel versus serial and some of the different USB speed stuff. I can see in, for Evan, maybe we'll throw a USB hard drive question on there, especially since he skipped today.
Yeah, really bad first day.
Yeah, seriously. He was beat up in the parking lot at Best Buy for, for selling somebody a bad keyboard. Tim Huseman's late too. They're roommates. Could have been some multi-threading going on. Totally recorded. I said only operating system appropriate stuff there. It was every one of those words is an operating system thing.
We're going to hell before.
I didn't say anything. You guys interpreted my words. I'm talking about multi-threading. It's somewhere on here, isn't it? Please be on here. Yeah. See, threads versus processes. All right. So USB crap. Interrupts. So this kind of relates to this bullet point above, the I/O and CPU execution correlation. how the CPU gets interrupted. And again, at the high level, kind of how expensive that is. And maybe that even connects up to this bullet point here, dealing with memory and CPU, how the CPU gets scheduled. So each process, each program gets some time on the CPU. Again, we've talked about this at the high level, not really specifics, but kind of balancing that in terms of making sure that the CPU stays busy as close to 100% of the time as possible, which is going to be one of the goals of an operating system, while at the same time not wasting a whole lot of CPU cycles switching between programs because that's expensive. So that kind of comes down to the constituents of it. Who are we trying to make happy at any given point in time? Keep the CPU busy, one of the goals, so on and so forth. So those things are all interconnected. Types of memory and storage. So that would be the whole rigmarole about hard drives versus the caches, the different caches, L1, L2, L3 cache. The roles of those different caches, L1, L2 being on the CPUs, L3 being shared between CPUs for multi-core situations. System memory, so the whole memory discussion of those different things we talked about. Then, of course, threads and processes. So the idea of spawning threads as well as forking. Abe?
Gotcha.
I have it in my notes like 11 times and highlighted.
More like 15.
I framed it. Are you supposed to remove these cups from the cafeteria? They let you take ice cream cones out. What if I eat the cup? Well, Tim just texted me. Let's see what he said. He's going to be a couple minutes late.
No, thanks for that.
Multiple CPUs, kind of the idea, maybe even the history of that, when we had two physical CPUs, then we got into single core. When we moved from multiple single core CPUs to dual core and even quad core CPUs. Even the discussion may be along the lines of, are more cores always faster? So certain problems benefit from having more than one worker on those problems at once. Other problems do not. Kind of goes back to our whole, how many so-and-sos does it take to change a light bulb? Whoever can change the light bulb individually the fastest is going to win that race, regardless of how many slow people you have trying to change one light bulb. Let's see. Clustered systems. So storage array networks, cloud compute platforms, kind of the exact same model, but applied to two different problems. One is computation and one is storage. But that was the conversation we were having related to like Google and how they have both. They have a compute cloud resource and they also have a cloud store, a data store resource, which is a whole bunch of storage across many, many, many machines that they duplicate a bunch of times. In that same conversation, we were talking about kind of the change in goals between maybe 15, 20 years ago and today, where 15, 20 years ago, memory was at a premium. So relational databases like Oracle, things like that, had a focus of minimizing the amount of duplicated data. Today, we don't care. Today, it's like, let's just duplicate the data 5,000 times so we have, faster access to it and, higher reliability, if you will, because we have unlimited hard drive space with these storage array networks and a big enough pocketbook. That's kind of the idea. Process management, kind of talking about that kind of goes into that same discussion about interrupts and things like that. How a process is born, how does it move from the hard drive to from the hard drive to memory, then ultimately to the CPU, that kind of stuff. Memory management, Again, all these at the high level. We're going to specifically talk about the details of, we'll spend a lot of the second half of the semester talking about process management, inter-process communication, and memory management. The details of those. File system management, we kind of gloss. I don't know, it's just boring. But as we were already seeing here just from this list, so many of these things are interrelated that when you learn kind of the way of sharing one resource, a lot of those lessons apply to sharing other resources, kind of the same stuff. Distributed computing, again, kind of the cloud stuff. Clients versus servers at the software and the hardware level. Peer-to-peer networks, so best way to steal music. Let's see. Command line versus GUI. Resource allocation, which really the study of operating systems is all about resource allocation. Everything that we do in operating systems is about, managing various resources so that as many people who care are happy at all times. You're here.
Yeah. Didn't you get my text?
I did. There was a rumor going around.
What?
You'll have to watch the video and promise you don't turn me into so.
Things that you told before.
Well,
and the
we
fact
just
that I haven't turned you in now.
as a group, we just noticed that you and your roommate were both missing today.
He wasn't even home like all week.
Hey, look, don't get defensive.
So I don't know where he is. He can make up all the rooms he wants.
It just so happened we were talking about multi-threading, and your name came up.
No. My reasoning is that my alarm didn't go off, so it's pretty shitty reasoning.
Seriously.
You can think what you want. I mean, I could have made something up, something involving 4 cars, a semi-truck, and a giant magnet, so it would have been more interesting.
Okay, what we're talking about. Peer-to-peer networks, how to steal music. Kind of the role of peer-to-peer networks in maybe kind of our early days of networking between PCs. And I say early days, but many of us still use peer-to-peer networks today. And so we can almost trace this historically from maybe day one being kind of the Napster world, and now today, many of us use BitTorrent, right, for various things, whether we know it or not. Whether you utilize BitTorrent, when people want to test to see how BitTorrent works by downloading illegal things that they'll just immediately delete from their machine, of course. You would download a torrent. So torrents typically have a negative connotation associated with them, right? But the reality is, if any of you play video games, and those video games have patches, when you download the patch, almost all of those now are utilizing BitTorrent technology. Rather than having a single server, at Blizzard or Apple, whatever. It doesn't have to be a video game. It could be a software update to an operating system or something. Rather than there being one single repository that everybody's hitting at once, it becomes a distributed network where you're actually downloading the portions of that software from this peer network where everybody's contributing. So for those of you who are, BitTorrent people, and you use BitTorrent for various good and bad reasons, I'm sure every one of you, is once you finish acquiring the software that you are after, the program that you're after, you always leave it seeding after that, right? So you're supporting the rest of the network. Or do you just immediately cancel it? Okay. Sometimes you wonder who the people who are seeding all the times are.
Typically it's like Brazil or Russia or something. Someone just
Or they don't care, or like
care.
their computer's in a remote location, and it's going to be 2 weeks until they hike back up there. I had a buddy who his son was a missionary in Africa, and So my friend's name is Fred Seton. He was like the director of IT at Western Illinois University. He's retired from there now, works at someplace in Chicago. So he's pulling a pension and working. That's the way to do it. But in any case, really, really bright guy. And he had written some program that his son, who's the missionary, was interested in. Well, no, it was the other way around. He had written a program and he had previously sent it to his son. And the program was for a Raspberry Pi for feeding his fish. So he took a Raspberry Pi system on a chip, system on a board thing, and built. I think he used a 3D printer to build this this wheel that, every single time it turned, it dumped a little fish food into the water or something like that. I have a picture of it somewhere. Well, in any case, his SD card for it failed or something, so he needed to get the software back, and he had lost it. He hadn't backed it up. So the only copy of this was a hard copy that he had mailed his son in Africa. So the next time his son went to the mountaintop to call, to call dad, his dad said, "Do you still have that program I sent you?" Because the son was interested in reading about it. So this was the joke he uses. This is a perfect example of off-site backup. So his son is reading him this program line by line via candlelight from Africa. So, I'm just telling you, a lot of stuff has to go wrong in order for him to lose that code. It's like, I use a resource in Africa for. Apparently, I think it was only like a 150-line program. It wasn't a major ordeal. We read the source code of an operating system via candlelight. Yeah, I don't know how I got off on that, but that was the whole peer-to-peer network stuff. Command line, resource allocation, system accounting. So this is kind of the idea. We kind of talked about this when we were talking about file systems, specifically journaled file systems, being able to roll back. So at some point, we have to have kind of a checks and balances system on our operating systems that kind of log the stuff that has happened, so that if something bad does happen, we can go and look and see what went down, and is there a way I can reverse this? That type of deal. So really, system accounting would be more of the idea of logging, that kind of stuff. File systems. What we talked about in some sort of detail in here was NTFS versus FAT32 versus UFS, Unix file system. Really, the interesting bits were probably NTFS versus FAT32 and the differences there, the strengths and limitations. Something came up was why do USB hard drives and jump drives typically come formatted FAT32 when all of our operating systems, all of our hard drives for, if you buy a new Windows machine, is formatted NTFS. Why was that?
It's universal.
Okay, it is universal, so it can plug into both a Mac and a PC. Where NTFS, it's not gonna swing so well. What's the limitation of FAT32?
Put a single file of less than 4 gigs.
Yep. So can't store files that are too large, and 4 gigabytes wasn't too large back when FAT32 was popular. 4 gigabytes isn't all that obscenely large today, right? Fairly common for us to download files that may exceed 4 gigabytes. Say you're downloading a movie or the ISO for a PlayStation 3 game, that kind of stuff. These can be 15, 16 gigabytes for a Blu-ray movie, that kind of stuff. Let's see. System calls. We talked a lot about this recently. Almost the life cycle of a system call, those various layers. So we kind of have like 4 or 5 different layers in there, depending on how you want to look at it, where you have the user program, which talks to some system calls, which talk to the actual low-level language, which actually talks to the drivers, which then talk to the actual hardware. So it's kind of a, there's several layers in there, and what role do system calls play in operating systems? Why are they important? The idea is that system calls over time typically remain the same. So, 10 years ago, Abe could have done some forking. And today, he can also fork. That system call has remained the same. Now, what's the advantage of our system calls remaining the same over long periods of time? Why is that a good thing? Old code still works. We can update how a system call works. But as long as the system call is the same as it used to be in terms of the name of it and what parameters it takes, old programs can still work in terms of those system codes, or those system calls. So it becomes a compatibility issue. Parameter passing between system calls, some of our various options for that. We talked about passing through registers, to passing through memory, passing through tables. So a couple different options, what the pros and cons of those are, that kind of stuff. Memory management, differences between MS-DOS and Unix. So that was really the discussion that we had dealing with the difference between a single user-centric operating system versus a multi-user-centric operating system. What decisions do they have to make? And we just started talking about that kind of at the high level. We'll kind of pick up there and talk about that a little bit more today to flesh out what you're going to need to know for the midterm. But at the end of the day, it really becomes this idea of in old memory management, when we're dealing with MS-DOS, we could literally, when we just had one program, not just one user to make happy, but one program that we had to be capable of running at once. We could just take everything but the special portion of the memory that had the operating system in it and just say, this is for running the program that you want to launch. As long as the program you want to launch will fit in the rest of memory, you're good. As we get to multi-programming operating systems, our modern day operating systems that allow us to have more than one program running at once, or even in the older days, multi-user operating systems where each individual user can only run one program at a time, now we have to start dealing with memory differently because we have to fit more than one program in memory. That makes sense? So that's really that discussion there where MS-DOS is a single user, single program operating system, if we go back to the beginning, and Unix is a multi-user, and maybe in this example, still a single program operating system, single program per user. Okay, so those will be the topics on the midterm. Again, it's short answer, essay type thing. We will not have any programming on this test. That isn't to say there isn't programming in this class. Second half of the semester, we're going to be doing some more of that. So, be prepared for that. It's always fun to write operating systems. Good stuff. So, in any case, you avoid programming on this particular test, but it will deal with some of the details. I would say as you're going through your notes, if we spent time talking about kind of some interesting nuances, even when I get off, on a tangent, obviously tangents dealing with like restaurants or baseball or something like that, probably not going to make the test. But sometimes I get off on a tangent, leaving the slide, but still talking about operating systems. Those are important concepts. I would say in many cases, maybe more important than, the theory crap from a knowledge-based perspective. All right, so questions about the midterm or questions about any of the individual topics here. I would suggest you maybe review them before class on Wednesday, and if you have some questions on Wednesday, we can spend a little time answering those. Otherwise, I'll just keep going with the notes. But everything you're going to be responsible for will finish today with well, we've really already finished it, but I'll flesh it out a little bit more with this MS-DOS versus Unix thing. So, questions about the midterm? Pre-bribes? Yeah. Friday. So then do we have break?
Yeah, I think that's
next week. When are we're off Thursday, Friday, and the weekend? Is that the break? Is that just made up? Something like that. No,
Friday.
midterm is Friday.
Okay.
This week.
I'm not gonna be here.
That's right, you told me. So email me like on, when do you leave?
9 a.m. is when the flight leaves.
9 a.m. Friday? So email me maybe Thursday morning or talk to me, and you can take it like later in the day on Thursday or something. We'll figure it out. But you're not allowed to undercut my bribe prices.
Bring you a pretzel pizza.
Well, no, that's not that far. I mean, see, I'm offering a value to students that want to offer me money for points on the test. And since you will have already taken the test, you can't undercut my prices.
When is this going right?
I can't advertise that on.
Just hand signals.
just flash the signals. All right. So,
Don't ask him to flash anything.
all right. So, any questions? We're good for now. All right. So that is the midterm. So here, just a couple, I'll just bounce back a couple of slides and rehash that last thing we talked about. So again, MS-DOS is single tasking, so one program running at once. The shell is invoked by the system boot. That would be like the bootstrap process somewhere in there. It's simple to run a program. The way we would organize memory is you would have your entire bucket of memory. So let's just use today's standards and say we have 1 gigabyte of memory. You would have not had anywhere near that back in those days. But you're going to take a little chunk of that, maybe 10% of your memory, let's say, and that's where the operating system lives. And that's dedicated for the operating system. The rest of the memory is going to be for that one program that you want to launch. So memory management in single user, single programming operating systems is very simple.
When is the space allocated for the operating system?
It would be allocated at initial boot. Yeah, when the operating system is getting loaded into memory, it would advertise its size. In fact, in most of the time when this memory management was being used, and this is really old memory management, so we're trying to apply it to a much newer way of thinking. The size of an operating system was kind of a set size. So maybe you would have 32K set aside for the operating system, and there was kind of a rule of thumb that the operating system had to fit within 32K of memory. Don't make an operating system that won't fit within 32K of memory because it won't work on the memory manager. Now, having said that, keep in mind that the software for managing the memory is part of the operating system. So the operating system should know how large it is, as it's booting, and it's going to say, okay, I'm going to treat this first however many bytes of memory big enough to hold all the stuff that I'm providing as the operating system. I'm going to go ahead and allocate that, leaving myself this for everything else. But it would happen as the operating system is actually launching and kind of bringing all of its systems up. So single memory space, loads programs into memory, overwriting everything but the kernel. All right, so that's MS-DOS, the most simple example of this. FreeBSD would be a Unix clone. Unix-based operating, it's not a Unix clone. FreeBSD is actually Unix. It's BSD-based Unix. The B stands for Berkeley. S is standard. I don't know what the D stands for. In any case, so it's a Unix variant. It's multitasking. But for this comparison, think of this multitasking aspect as multi-programming from the perspective that each individual user can run one program. For this initial comparison. Certainly our modern day Unix operating systems are multi-user, multi-programming, multitasking. So every user can have multiple programs running at once. But for this comparison, let's just think about some of the problems that we would need to solve between supporting one user with one program and supporting many users each having one program. what decisions have to be made there. So when a user logs in, that's going to invoke the user's shell. Whereas with DOS, you're automatically logged in. It's a single user machine, and the shell just launches. The DOS prompt just launches. With Unix, there's actually even a layer here that we're not even considering. With a multi-user operating system, especially a long time ago, you would have when we think about a single user computer today, you just sit in front of the physical computer and use it. Well, with Unix, if you're going to have multiple users logging in, today we don't think of that as being a major challenge. We can all log into Amazon or, something like that, and we just sit down in front of our computer, hit the web browser, and now we're all logging into that central computer that is Amazon. That didn't exist back then. In fact, the idea of, these things existed pre-internet. Any of you remember before there was the internet? Were we alive then? What year did the internet first become kind of a thing? So I would say internet first started being something like people at home would have, probably like 93, 94, somewhere in that ballpark. 1993 maybe. Any of you alive then? Just real young. So, these are decisions that were being made pre that. Before we just sat in front of a computer and didn't think twice about remoting someplace else. So now we're sitting in maybe a computer lab where there's a terminal server somewhere that has the Unix operating system on it, and then a whole bunch of physically connected keyboards and monitors. At reference, we have a little mini mock-up of that in the lab next door. But these guys were, you had to be in physical proximity to the machine and close enough for a wire to reach to it. You just have a whole bunch of cables running to all these machines. So you weren't leaving the lab, but you could have multiple people all using that computer at once. So given that, you would have a limitation, a reasonable limitation at least, on the number of users that would be using the system at one time. And that limitation was really set by a couple of different things. One of the limitations was set by the physical number of connections that terminal server could have coming into it, right? Now, how many people connect to Amazon at one time? Thousands, potentially. And all that connection comes in through an Ethernet port. One little connection. One little connection can support, let's just say, an infinite number of simultaneous connections. Well, that wasn't the way it was back then. The way it was back then is you had one incoming port per person connected. Even in the early days of the internet, we had this problem. Now we open up our laptop, in theory, Concordia, we open up our laptop and hope we can hit a web page. But we open up our laptop and we just go to the web page. We don't think twice about it. Well, in the early days of the internet, you would open up your computer and you would connect it to the internet first. That would be your first step, is let's connect to the internet. And in the beginning, you would connect to the internet through dial-up modems, right? So you have this little machine that uses your phone line. So that's a physical connection coming to your house. So every person that was connected to the internet had a physical line coming from their machine. Now we still have that today. We have a physical line coming to our cable modem, or a physical line coming to our DSL modem. So we made that dial-up call. Well, that phone call went to some bank of modems. There had to be one modem on the other side for every one person connected. So you might run into a situation like I used back in Champaign, Illinois, kind of in the early days of the internet. We had this bulletin board system, BBS, called PrairieNet. And PrairieNet, they would have some dial-up modems. And I think there was probably a total of like 24 people that can be on PrairieNet at once. Then they ran out of modems. They didn't have enough open modems for you to dial into. You get a busy signal. But before that, you would dial into a central bank, which then divert you to one of the available modems, and you would connect. So you would try to hog it. And if you couldn't get on the internet, think about it today. How many of us are addicted to the internet today? Without even thinking about it as an addiction. It's just kind of like normal way of life now, right? What if, even now we're like switching Wi-Fi networks and stuff like that until we can get a web page to load. It's like, I don't even need the web right now, but I just want to know it's there. It makes me feel all warm and gooey. I mean that, Tim, in a Evan kind of way.
We'll relay that message when I see it.
I didn't say anything. You guys took it in a weird way. I don't. It's a Christian university, people. What was I talking about? Oh, warm and gooey. What was I talking about before that?
I've already been damned to hell once.
Yeah. Okay, we were talking about the dial-up modem. So you would sit there if you couldn't connect, and you would just keep trying to connect over and over again, waiting for the busy signal to go away until you finally got connected. And then if you were in the middle of playing a game or something like that, and you got disconnected, you better hope you could reconnect. You might hit busy signals, and now you're out of the game. So that was how the world worked back then, even in the early days of the network. So we're talking even before that, where you had to have physical access to that machine, and the number of modules, the number of users that can connect to the machine was limited by the number of physical connections that machine had. Maybe that's 8, maybe that's 10, maybe that's 30, something like that. Now, the next thing that limited how many users can be connected at once, besides the physical space, was the processing and memory. Memory was very expensive. Processors were expensive back then as well. Less expensive, relatively speaking, than memory, but still expensive compared to today. Today, the price of these things have come way, way, way down. But even that one machine, that one Unix server, we might say, okay, it was a server class machine, so it probably has more memory in it and a faster processor in it than your typical desktop DOS machine made for one user. But realistically, how much more power does it have? When you think about servers and server class machines and user class machines today, how much more power does a server class machine really have in it than our typical user class machine? Those of you who are building your machines for gaming and stuff, you've really built, by most definitions, a server class machine. You've probably put a pretty beefy processor in there with a large amount of caches, L2 and L3 cache, which is just going to help your multiprocessing for your video games. But those exact same features will also help that guy be a beefier server. Well, so let's take our latest, greatest, coolest gaming machine, and then let's take the budget pleaser HP desktop computer from Best Buy. How much more powerful is that gaming machine than the Best Buy computer? It's hard to kind of measure that, but if we were throwing a number on it, you think maybe 3 or 4 times more powerful? Something like that, right? Not hundreds of times more powerful for a physical server. Well, now that becomes an interesting thing. Can we run a Unix server off of, so we'll take your gaming machine. Could we run that as a Unix server? Absolutely. Throw Linux on there. How many users could you, if you wanted to run a web server on his machine? I mean, we're not going to be supporting eBay or Amazon or Google with that, but could you run a reasonable website off of your machine? Probably handle many, many internal simultaneous connections? Yeah, absolutely. The machine would be able to handle that. No big deal. A lot of internet providers today offer static IP addresses if you want to pay extra. So you can actually run a server out of your house using something like that. Well, at that point in time, his machine just changed its roles. It's running that Unix operating system, but it's trying to please a lot of incoming web connections at the same time, as opposed to having to just make him happy playing his one video game at a time. So the goals of that operating system has changed, and that kind of goes back to one of the topics for the midterm. We have to think about goals in terms of what the job of that operating system is. Even for that, we talk about multi-user systems. Well, now we got to talk about the applications. If you're running a web server, typically you're handling many small requests, right? That's what a web server would be. Give me this web page, give me that web page, give me this image. Okay, lots and lots of little tiny requests, as opposed to somebody, a group of people using a Unix server for productivity, where they might launch a text editor and be in it for 2 hours. So now that web server, or that server, has to give that one user its attention, whatever that means, for 2 hours. Problems become interesting. All right, so we'll stop there. Come back on Wednesday. If you have questions about the midterm, I'll take those at the beginning. If you want me to clarify anything, I'm happy to do that. Otherwise, we'll pick up where we left off here. But anything we talk about on Wednesday new will not be covered on the midterm. All right, I will see everybody on Wednesday. Remember, if you're able to help either tonight or Wednesday or both, moving some stuff, let me know. No pressure, but you'll get a meal out of it or something, and whatever.